Hello everyone, welcome back to another GIS lecture video. And in today's lecture video I want to talk about error in GPS. More specifically talking about why this position that we find with trilateration is never perfect. And what I want to do is start off from where we left off last time with this idea of trilateration being the distance from a minimum 3 in 2 dimensions and a minimum of 4 in 3 dimensions. Satellites that are beaming both their position and the time that they send the signal, and that we're using this equation distance equals velocity times time to figure out this distance between them, and that we're using the place where that distance overlaps for all of our pieces of information to calculate our position. So let's go ahead and give ourselves a little bit of space here. Okay, and let's begin another diagram. So this diagram, what we're gonna do is we're going to have U. Actually, let's go ahead and use a different color. Let's use green. Green seems like a good color for this. All right, so we have U sort of standing on Earth. Right, so this is going to be U. All right, this is U. All right, and you have your little receiver here, and it's calibrated to detect signals from all of the satellites that are in the orbit of the Earth above you. Now, to make this more realistic, what we have to include here, and this is something we haven't talked about yet, is that the Earth isn't just you, right? It's not just your car, right? There are buildings. Actually, let's make the buildings. Right, there are buildings, right? Maybe you're standing next to a particularly tall skyscraper. Right, maybe you're standing in a wooded area and so there are trees around. Right, so there are trees around. Right. And more importantly, also too, something that we haven't talked about yet, and we'll talk a lot more about this when we talk about remote sensing, but the idea is that the satellite itself, let's go ahead and draw the satellite here. Right, the satellite itself, right, is out in space, right? It's orbiting the Earth in space. And so these communications, right, that we've talked about so many times before, right, this data, this electromagnetic radiation information that's passing back and forth, right, is traveling from space where it's being produced by the satellite to the receiver on Earth. And in order to do that, right, it has to pass through the atmosphere. Right, it has to pass through the atmosphere. Right. So in order for the signal being sent from the receiver, or from the satellite, it has to go through the atmosphere to the receiver. And this diagram is going to allow us to talk about all the different kinds of error that can occur in GPS as to why our GPS signal isn't exactly perfect. And basically there are 3 categories of error. There are the error that occur at the satellite, there's errors that occur in the atmosphere, and then there are errors that occur near and at the receiver. Okay. So let's go ahead and talk about the first category of errors. Actually, let's go ahead and let's give ourselves a heading here, right? Errors in GPS, right? And again, I'm using GPS here as the American example. Global navigational satellite systems, these same things would apply pretty much universally. And so there's 3 categories of errors. Let's first talk about the errors that occur on the satellite. Well, the first error that can occur has to do with the position, right? Because I said that the satellite is sending two key pieces of information. It's sending its location and the time that it sent the message. And so you can imagine that there could be a problem with both of those pieces, right? In the first case, right, we know the position of the satellite based explicitly on the physics of the orbit of the satellite. Well, what if that was wrong, right? It can happen. What if we calculated the orbit of this satellite slightly incorrectly, right? What if the satellite is actually here, right? And I'm going to do this in a slightly different color so you can hopefully see just a little bit different. So what if the satellite is actually here, but when it broadcasts the signal, right, it says that it's actually here, right? This is the wrong position, right? So the first type of error that can happen is where the satellite actually sends the wrong position. And we call this an ephemeris error. Right, we call this an ephemeris error. And an ephemeris error is basically just an error where the satellite sends an incorrect position, or the position of the satellite is wrong. Right? Basically, the satellite sends an incorrect position. Right? And you can imagine if we go back to that concept of trilateration, where if that center of the circle is wrong, right, that's going to throw off the entire calculation, because now our distance, even if the distance itself is correct, right, that starting SERP point is going to be wrong, which is going to completely throw off our calculation here. All right, so ephemeris errors are errors where basically the satellite, when it sends the signal, sends the wrong position. So we're actually starting from the wrong place. In a similar vein, right, another error that can occur on the satellite side is we have what are called clock errors. Right? And so these are essentially the same as the ephemeris error, where the satellite sends the wrong time, right? Or there's a miscommunication in the time. Right, the satellite sends the wrong time, or there is some other sort of issue with the timing being incorrect. And just to recap again, the equation here, we're using distance, right, equals velocity, which I'm going to switch to c, which is the speed of light, times time, which is based on the time that the signal was sent and the time that the receiver received the signal. Right, so you can imagine here we're talking about an extremely high velocity, right? Light moves very, very, very quickly. So even if you were off by a fraction of a second, right, that could mean miles of error in this equation, which means miles of error in terms of where we position ourselves. All right, so these two errors here, ephemeris errors, which are the satellite sending the wrong position, and clock errors, which are issues where the timing is incorrect. Right, these two errors happen mainly coming from the satellite. Okay, so let's talk about the next set of errors, which are atmospheric errors. Right? Because again, right, we said that the atmosphere is interacting with the energy. Right? We'll talk more about this when we talk about remote sensing again. But basically, you can imagine the satellite is sending its signal. Right? That signal has to pass. Actually, let's do it from the right position. Right? It has to pass through the atmosphere in order to reach the receiver. Well, atmosphere is matter, right? Just like you and I are matter. It's made up of different molecules that predominate the atmosphere: nitrogen, gas, oxygen, right? Various particulate matter, right? And all of that is going to interact with this electromagnetic radiation, right? In the same way that you and I interact with electromagnetic radiation. Right? So within the atmosphere, right, two things can happen. One, the signal can actually be bounced around, right? The signal can be kind of bounced around, which would increase the length of the path, right? It would increase the distance that the signal had to travel artificially because it's zigzagging instead of going in a straight line. And so when it does that, right, that increases the amount of time that it took to reach the receiver. And when you do that, right, because we're sort of assuming, and if you remember back to our trilateration diagram, right, we're sort of assuming that this distance from the satellite to the receiver is a straight line, right? We're not accounting for any of these deviations here. So we're artificially increasing the length of the path, right, that this signal had to go through to reach the receiver. And when we do that, we increase the time it took, which means we're going to calculate a distance that is going to be incorrect. So we call this one of the atmospheric errors. We call this atmospheric errors. And that is basically when the signal interacts with the atmosphere in a way that reduces the speed, or I shouldn't say reduces the speed, that changes and reflects and bounces the signal around, delaying the signal from reaching the receiver, right? So this is when the atmosphere interacts with the data signal. Let's give ourselves a little bit more space here. Right, the atmosphere interacts with the data signal, reducing its accuracy. Right, again, because you have to realize that what's happening here is it's physically delaying, right? It's delaying the signal from reaching the user. And because we're not accounting for this, right, it's going to artificially increase the time, which is going to artificially increase the distance. So that's atmospheric errors. So now we've managed to get from the satellite, we're going to assume that it's in the right position, that it's sent the right time. It's bounced through the atmosphere. And we now have hit the sort of ground level, right? So now we're sort of where we would be. And we realize something, right? We are surrounded by objects, right? Buildings, trees, whatever. And this is going to interact in much the same way that the atmosphere did, right? Where it's going to hit buildings, it's going to bounce off, it's going to hit a tree, it's going to bounce off before it finally hits the receiver, right? So this is essentially the same thing that's happening in the atmosphere. We call it, when it's in the atmosphere, we call it atmospheric errors. When it's happening on the ground, right, when it's happening where you are, we call these multipath errors. So I'm going to go ahead and make a note down here under here. Right, we call these, let's switch back to white. Right, when it bounces off of trees, buildings, real-world objects, right, we call this multipath errors. Multipath errors. And again, this is basically just saying that the signal, once it reaches ground level, is still going to be bouncing off of objects, right? So this is basically interactions with other real world objects, right? And this is much the same as the atmosphere, except it's happening at ground level, right? And the atmosphere is bouncing around, we call that atmospheric effects. On the ground level, when it's bouncing around, we call that multipath errors. But it's essentially the same thing, that the signal is being delayed artificially because it's interacting with things other than the receiver. Okay, so there is one more type of error that we need to talk about. So we've talked about errors at the satellite level. That's the positioning, the ephemeris, and the clock, where we might have some issues with the signal that it's sending. We have the atmosphere bouncing the signal around and delaying it before it even reaches the ground. And then once it reaches the ground, it bounces around off of real-world objects. But there's one more error that's actually located directly at your receiver. Okay? And we call that error receiver noise. And I'm going to try and diagram this with some little red things coming off here. Some little red sparks coming off here. All right. The last error we need to talk about, I'm going to move a little bit to the left here. Okay. The last error that I want to talk about is receiver noise error. Right, receiver noise error. So this is the last type of error, receiver noise error. And so as the name kind of implies, right, we have receiver, meaning it's happening at the receiver, and we have noise, meaning that the receiver is making some kind of noise. Well, it's not auditory noise, like it's not buzzing or humming that you would hear, but you have to think about, again, the fact that this whole signal here is electromagnetic radiation, which is some wavelength that is being produced and received. Well, according to the laws of physics, right, anything with a temperature greater than 0 Kelvin, absolute 0, right, produces electromagnetic radiation. Now, the peak wavelengths that are produced vary with temperature, but the thing is, when you start getting into the electronic circuits inside of a receiver like this, right, it's going to be producing at a small level some of the same wavelengths that this signal is producing. And so what happens is, internally within the receiver, right, it is producing basically signals that are similar to the ones that it's receiving in terms of the wavelength that interfere with the actual signal, reducing the quality. Right, so receiver noise error is basically the fact that the receiver is producing its own electromagnetic radiation that interferes with the signal. Right, the receiver produces its own electromagnetic radiation, which I'm going to put as ER for short. Electromagnetic radiation produces its OWN, own electromagnetic radiation that can interfere with the signal. Right, and so that's basically, again, receiver noise error is the fact that this is producing electromagnetic radiation to communicate inside of the receiver. The receiver itself is also producing electromagnetic radiation, and that some small portion of that can interfere to some extent with the actual signal that we're trying to read. Okay, so hopefully that all makes sense. So let's go ahead and let's just recap the errors that we have. We have ephemeris errors, which are the position being incorrect. We have clock errors, where we are sending or receiving the wrong time. We have atmospheric errors, where the signal is actually being delayed in the atmosphere. Then we have multipath errors, where the signal is being delayed because it's interacting with other real-world features. And then finally, we have receiver noise errors, which are basically errors that are caused because the receiver itself is producing radiation that interferes with the signal. So between those 5 errors, this explains the vast majority of the error as to why our little trilateration example is never going to be perfectly accurate. So in the next video, we're going to take these 5 errors and we're going to talk about how we can actually work towards improving them, and in the case of some of them, why we can't improve them. So let's go ahead and end the video here, and if you have any questions, as always, please reach out. Thank you.